Welcome everyone to another FPGA live stream here, having fun with the previously unboxed and getting started and Pico RISC-V and so on from the previous live stream for our not only learning and mastering FPGAs and Verilog and such, learning new things, having fun for, well, my fun and your education, or also your fun. And if you're interested in the details, there are already 3-4 previous live streams. Today I only wanted for my after work 20% or whatever project here have text mode output on the HDMI. Of course, here's an HDMI example coming here with 1-bit squared icebreaker with Clifford Wolf's Pico RISC-V. So let's power this up. So this is an example that comes with it. Also here only live with this light, and of course we have actually right now not so much to that. Can we also so it takes a couple of seconds for this, by the way. This is slightly off anyway. So this is some example which can also toggle here with, which by the way we also have fun scenes somewhere here of that or that sort. Can toggle this example toggled. Anyway, these are the examples. The commercial bunny only frame grabber here, maybe not the most snappy. Anyway, this example is of course impressive for FPGA goodness, totally amazing stuff, but we certainly want some text mode or other graphic output here for our Pico RISC-V core. And today here on my after work project I've just done this. I started this, so it's partially working, so finishing that another day, like tomorrow. Anyway, let's show you what we have done. Also, cable right now a little bit. Anyway, so this was this example. Let's go here to our tweak. So what I've done, I've simply deleted everything I didn't need here. Icebreaker examples tweaked, DVI 12-bit. Also, it took me, so I think this example is 1 pixel shifted off by 1 with some clocking details that is upstream. I only realized this after tinkering 1 hour. Why is my stuff 1 pixel off by 1? But that is a generic challenge there. It's certainly like clock signal related. Let's make here and flash my example. So right now, and actually this boots up rather quickly. Slightly wonder why this boots up so quickly. Anyway, so this is my text output. I've not shameless stolen this somewhere else. And I only inspired and Googled my rusty Verilog knowledge. And so as you see, these outputs are to T2 with a space T2. So let me show you how this works. That you learn something. Why do we do this? We have also Clifford Wolf's amazing Pico RISC-V. Oops, not that we short here something with our precious. This is still hopefully running. I hope so. Again, we want to build as a fun with the FPGA our homebrew Pico RISC-V, also amazing RISC-V, goodness, not this rubbish Intel CPUs that don't even have a working jump instruction. So totally open source and also contributing a little bit and certainly learning ourselves and learning and having fun ourselves and entertaining, and hope that you also learn something. So this is a FPGA board and we are slightly constrained with the 5K 5280 logic cells, the 120K dual port block RAM and the 128. This is storage. Where is, let me, here one, so single port. So we have 1 Mbit single port memory and 120K bit dual port. Of course, constraints single port, dual port, that you probably can access this concurrently. So here's my code here somewhere in either this. This is how Verilog looks like, and either was it in this file also. What I've changed, so there are still some challenges ahead. However, this took me already like 3 hours just to get this state, just for your entertainment and learning experience and having fun here. Welcome Christian. So it's not yet fully done. So this is a working proof of concept. I have some challenges. So again, let me check the scene here. So I've taken this line drawing example, and which probably we can also open for you. So this is VGA core. Let me also see what we have in the command line to show you the difference. So that is tweaked. There are still some challenges ahead that I will tell you in a second. Examples, HDVI 12-bit VGA core. So the original code is noteworthy that the original code does not use any video memory. The original code is generating this here. Here is a proc output. This is a mux, a multiplexer that is switching between the demos, the test pattern, the demo, the ball or the line, and none of this, all of those demos work without video memory. As crazy as it might sound, what the code is doing is for each of those pixels, this is just the multiplexing procedure. Here, for example, the moving lines, and depending whether this mode bit is 0 for initialization, and then later if it's not 0 for actually drawing this, and this code is just comparing the position. So this is completely video memory less video signal generation, in that the line is only comparing for the currently drawn X and Y position, and if this position here is the line X position, then it is setting this to this changing random color here, and also the ball. So this is not unlike, and this is the complete difference of FPGA logic cells and CPU. In a CPU you would always, the CPU could not even generate this test pattern so fast, especially this 12 to 40 megahertz CPU in real time. So that is why on a 386 or Pentium of failing Core i7 and Core 9 stuff today, you would draw this slowly in a video memory buffer and scan it out. This is why it's called scan lines or scan buffer. Scan this out on the video graphic array, and the FPGA can do differently. This is running, not only are all those logic elements running in parallel, also 5000 of it, but we can do this in runtime, compare it each pixel with the logic elements, compare the position and set the output. You couldn't even do this with the CPU like that. And so this is why my code changed entirely. I only wanted to show you the original code here, that it was memoryless. And so it took me a while. So initially I even didn't use it like this. Took me a while to figure out, because most of the proprietary commercial examples work slightly different in instantiating the block memory. This is why I couldn't directly use those examples for the most part, and it took me a little bit of trial and error here, inspiring from Clifford's. Also, there is apparently some block RAM delay initialization. So apparently, so you can initialize on the FPGA, you can initialize the memory to something, and apparently there's some initialization delay of some clock cycles of whatever, also fun stuff that you find. So I only inspired here how to define larger resources. It took me a little bit of Googling and trial and error. And once I figured this out, because so initially I only had like one character as a test pattern, and I was only outputting R, obviously, because we are here on my channel. So initially I didn't have any of this stuff. And in the output routine, so I deleted all of the line and ball and stuff because I didn't need this. We have here only one procedural VGA output here with for each positive edge of the pixel clock, scanning this out to the HDMI transmitter here on this PMOD here of this scan out frame. And so initially because initially I didn't know how to use the block memory here on the FPGA for a real actual screen buffer, I used here simply, I cased here, that is how it also works in Verilog, cased here the X position, and then assigned here this text 0. I had to I only left this here for illustration purposes. I had here text 0 here, like I had here 8, just 8 of this local parameter bit pattern, and I had hard-coded like scanning out this test pattern all over the screen for a test of it. And then was the longer part of figuring out how this ROM stuff works and how to actually initialize this. Yes, FPGA here of this FPGA goodness is what we generate this amazing, is it this or this? Oh, so many scenes. So this is right now, I can actually theoretically, let me, does it probably flicker when I take the power off? Or let me take, let me, don't want to pull on this. Okay, fine. You're only live on this channel. Let's pull this out. You see that is that signal, not faking that. And yes, on the FPGA for our homebrew microprocessor FPGA project here, because we want to learn everything, digital self-reliance. And welcome everyone. Also Glauco, thank you. We're doing fine. Hope you're also doing fine. So initially I started here then with a ROM and so some register with 8-bit 0 to 7 to 0. This, I named this ROM. We will probably rename this to font, but just for the sake of it, I had here ROM. This is just the font, and also we could initialize this. I also figured out this from Clifford's example there. We could actually initialize this from a file. That might be more convenient than typing all this, but for a quick test I typed this in here. Initial ROM 0 here. These are just font data, like in your VGA card's video BIOS for the font stuff. Right now, just for the test of it, an 8x8 font. This is why it looks so shitty, because whatever. I just typed here some zeros, and yeah, so ROM 8 bits of binary defined goodness here, and are also, yeah, they are not properly indexed, so at position, because I just wanted to test here all this Verilog stuff. Of course, for reproduction stuff, nobody stops you or me to do this here, copy and pasting some more amazing font. And in the right ASCII layout, right now I only have here 4 or 5 text glyphs in here, and R, as you can see, and 2, so R2, T, and the space, because certainly we recycle the 2. Although the space I didn't even have to initialize, because it's probably all 0 anyway. And then later, so initially I only had here the text glyph, the character, static character ROM, only then later, because then later I added the screen here. So for a text already, I made this 2K large for an 80 by 24 text memory, and initialize this here to 01200313, which is here indexing into our BIOS text data. Indexing the 0 is an R, so R2 T, and then 2 again, space, T2 space. And step by step I changed here the code. You see I left it here for illustration purposes only. Initially my fixed test pattern for you at home to play along. And then later I was trying around here. In the meantime, all the commented out code is just my previous code when I was prototyping this. So what I do also, this is already including some optimization. Initially I had it without this if, and this is here, this character is a local register here. This is our raw and character, the bits in the character raw, and the bit pattern and the character. So the character is loaded here from our screen. This is our huge memory of text buffer. And we load this here for test pattern with a currently drawing from the VGA HDMI core from the example. Also, yeah, the naming is a little bit, yeah, I don't know why the naming is so strange. It's not my naming. Probably have to redefine this. Probably would call this VGA PXY or something. Anyway, because we divide this by 8, shifting it 3 bits to the right, and ending this with 3 bits binary defined 111. This is standard Verilog stuff. That is how you define. We could also define this 8-bit and decimal, hexadecimal, but we want 3 bits binary 111. And because we have here some timing issues, so I'm not pretending that this is still all amazing. I can show you next. Because when actually initially I wanted to have there this in X position, a text like hello world, here on this scan out, and because this doesn't really work yet, and I do not yet know why, I changed it to the Y position. So this Verilog code works in principle, just not like fully. There's apparently some timing glitch. There you see hardware not only Intel cannot do conditional jump instructions, also we, decade later after university, getting into Verilog again, some timing glitch. I can show you in a moment how this looks. This is why I optimized this, because I thought, okay, let's not load this from this register or this block memory or whatever the Yosys synthesis is placing our FPGA cells here. The screen, let's not load this for each pixel. That's of course wasteful. Let's only do this for each beginning of the pixel, because we have pixel 0, 0, 1, 2, 3, 4, 5, 6, 7, and all of those 7 pixels are of course in the same text character. This is why I try to optimize this here. Also, yeah, there you see how all the details of optimization and stuff not yet working. So this is only for the beginning of all the last bits 0 of our text character, only then loaded from the screen memory. And also probably later this is actually maybe usable, this optimization, because maybe later we also want to have colorful stuff, so that we have the similar to a VGA card of ATI and all the IBM goodness there, and load a text attribute of color and blinking and whatnot. And so yeah, we load this character here. So this is assignment of one register from another. So this is very standard Verilog code. You see it's not too dissimilar to C or something. Screen indexed here by our Y coordinate. Also I messed this up here because probably typing around here. Then we have this is our text, like hello world. And then of course we have the text glyph here to scan out the text character. So row 1, 0, 1, 2 and so on. And then depending on which Y coordinate we draw here, I index here the character into our text font memory by the character position multiplied by 8, of course shifting this 3 to the left, and ORing there on top the Y position for the row we want to scan out. You see previously I had this here coded, and then wait a second, are we doing this too often? What are we even? Wait a second, is my optimization not even working because I didn't comment this out? That is funny. Let's resynthesize this and program this again. The good thing is this small example doesn't take too long for Yosys to synthesize, optimize, pick and place, root and program here on the FPGA. We can also somewhere, you see the pattern will disappear, and then this is reprogramming, repairing. Okay, this still works, amazing stuff. And actually the edit compile time is not too bad. And also why, if we would synthesize all the Pico RISC-V core, this would on this Mac Mini, you've seen this in the previous live stream, take 10 minutes or so. That's certainly why you want to use an AMD, EPIC AMD Ryzen or something, or some Threadripper, because then the synthesis time of Yosys is probably coming down from 10 minutes to 30 seconds or something of that sort. Anyway, the cool thing is we can develop this modules, this Verilog modules here independently. So while we later integrate this to our Pico SoC with the RISC-V core for programmable retro vintage fun nonsense of whatever epicness you want to program there and play along at home. And by the way, if you want to play this at home, right, it's super dirt cheap here, $69 or $79 something, plus the HDMI. So yeah, $100 euro something, so that's what plus minus for the setup. This probably means, as I didn't have this commented out, let's try. So you see this works. So then I also draw here, you see I draw here a test line. So because I noticed eventually this is off by 1, the whole screen. Also not sure, the problem is I'm right now not seeing this entirely myself due to the nature of the video capture here. But on my HDMI display right now I only see it with you in the OBS live broadcast capture stream here. Right now I'm not sure if it's off by 1, so this is why the first pixel I draw here a white line just for me to check, because again there is something in the regular HDMI example driving core that probably we want to rewrite another day. Anyway, so this is optimization. Wait a second, did we comment this out or what have I even done there? Row. Wait a second, did I not comment this out? What have I even done there? Anyway, let's flash this again. Let's take a look on the comments. This is like radio, television for cool people like sadly still liking it, sadly still working. Okay, thanks for watching this at home. Welcome. Yeah, I will soon join the Discord more. So what have we reflashed here? Okay, this apparently is still working as far as I see. Apparently my optimization code was not, probably not working because I reassigned this here anyway. Also, you don't see this. Let's test here this, because the optimization I've only done because with the X coordinate, it doesn't work. We get some timing gibberish there. And there you see hardware is difficult, not only for Intel, also for Verilog relearning noobs here like ourselves. But you see unsuccessful people like myself can do this, so you can also play along at home if you ever wanted to program your own hardware stuff. And yeah, you see this is a little bit glitchy. And I'm not yet sure why. I think this should probably work. We can also theoretically zoom this probably a little bit in. Let's, did I lock this or? Yeah. Let's make this somewhat larger. And you see this is off by 1. Oops, sorry. As you see here, the X and Y should be white, but it isn't. So this certainly is off by something. And unfortunately now with this OBS stuff, I don't see it so precisely myself due to the nature of this capture. You see the hello world R2D2. So now we take the characters from the X position, and this obviously is a little bit glitchy, and I'm not really sure why. This is why I already optimized the loading of the video RAM, but as you see, it's not yet perfect. But I wanted to share this already anyway to keep you updated on the progress, that this is really doable. But next I might actually, so also we will share this code, so sometime soon I will release this on, by the way, probably we can center this transform center horizontally. Amazing. So sometime soon, you see, this is the hardware development is difficult. Certainly, probably more than it's still somewhat software, but different software. So next would be to scale this up, find some off by 1 issues. And not really sure why this happens. So what is strange is I think this is a timing issue. Maybe this is in general with this VGA core example. Maybe this now takes too long, and now if we take a look on this pattern, I mean, you see you can somewhat read R2 T2 T2, but it's a little bit garbled. And when the pattern certainly is okay. And when we flip this to Y, this also works, as you've seen previously. And my theory is that now maybe this takes too long. Maybe this, because this is a relatively high frequency signal to the pixel clock, is quite some megahertz. And maybe the example that I based upon is already not perfect. And maybe this is also why it's off by 1. From the original example, because loading this or computing the signal propagation time of these wires and logic elements takes too long for the pixel clock, and maybe this is why this is a little slightly garbled. Then when we load this for each x pixel, the signal is not, the output signals are not stable enough, or in this clock output nanosecond of clocking this out to the HDMI transmitter. Maybe this could be, I need to get more into Verilog again, and maybe this could be changed with this edge here of this clock dot, because at each clock, pixel clock, we also compute here the X and Y position, and maybe this could be done like on the negative clock, so like decoupling this a little bit of computing the next pixel on the negative clock or something to have the bit pattern more stable assigned or something of that sort. I certainly need to play around more in depth with just this example. Even already I noticed, after I noticed my example is like 1 pixel off, I checked, well, how the heck did this happen, and I flashed the original example. And if you run the original example, you see that the lines are also already, the first pixel is 1 pixel off. Or actually I think the whole picture is like offset one pixel or something. So whatever timing wise is going wrong there. Anyway, this works in principle. I hope this timing wise it is doable. I will change some things so, because here are some constraints that I called out already on the previous live stream, which is we do not have so much memory here on this probably somewhat entry-level FPGA. You certainly, the larger the FPGAs, you get super large FPGAs, but then they cost like $1,000, $2,000. And this is of course an entry-level FPGA for just $5 or $10 or something. This is why we have only 5,000 logic elements, only, which you see it is enough not only for Pico RISC-V core, but also all the other surrounding Pico system on a chip stuff. So we have only 120K-bit dual port block memory and 1 mbit, which is, mbit is certainly 4 bytes, you need 8 bits, so this is 128K byte, and this is 20 or so, what is it, 28, I guess, K byte. And so we are a little bit memory limited here for our small homebrew example. So I said this already in the previous video, that we need to optimize this quite a bit to keep the memory utilization, because to keep this memory utilization down, because the Pico RISC-V example is already using all of this 1 mbit. We could maybe reduce this slightly, but probably we won't. So we probably want to use all of this dual port block RAM, maybe, or most of this for the video core. And this means that we will probably as a maximum use, like only allow like VGA 8-bit like 320 by 240 or something, which is 64K, because we also need some of this block RAM. We also need for other stuff, like other registers in the serial driver, the Pico RISC-V core, and so on. So we cannot use all of this even for memory. So I will probably, right now this example is running at 800 by 600. I will most likely reduce this to 640 by 480 for our homebrew microprocessor example here. And then I will most likely try to allow a pixel 8-bit palette, like 8-bit 256 colors, just VGA standard mode from back in the day, at a maximum of 320 by 240. That is already more. This is already 72K. I'm actually not sure if we will have enough memory for that. We will see. If we do not have enough memory for that, I will decrease this slightly to 320 by 200 or something, what most games used anyway on DOS for the vintage stuff. But another challenge will also be, so right now, so the next challenge is to get this 100% working. I only wanted to share the steps on the way to motivate you, that you not only see some progress and see also the challenges. My opinion, it's also interesting to see the challenges. Because if I sit here 1 week and get this in total amazing working order, not only do I myself forget about the glitches on the way, but also you see in 2 or 3 hours at home, playing along at home, you probably can do similar stuff. And the next challenge will be integrating this with the Pico SoC that we previously flashed onto there, because I thought it is as simple to, the Pico RISC-V, of course, being here somewhere of, anyway, that sort here, this here, and also quite readable Verilog code. and picosoc that we previous video synthesized and flashed onto there. Here of course are a couple of files like icebreaker, Verilog and picosoc, Verilog and simple UART for our USB output there. And I thought it is as simple because the HDMI output is not like conflicting with any of those resources, like the pins, like GPIO pins here for using those for the pixel clock and stuff. And I thought it is as simple as dropping my VGA core examples in there next to the picosoc and adding this to the make file and making sure it's called during the synthesis. And it is called, it's there, but somehow my VGA core is not used, so I'm not really sure why. Maybe because this example is larger, maybe I need to instantiate it here in the picosoc here, instantiating this stuff here. Maybe this is just missing, so integrating this will be the next challenge. It's not throwing an error, but my VGA stuff is not there, so yeah, that is some challenge for another day. And then the next thing is connecting this on a bus, because even if this would work right now, it would not be integrated. So if we just throw in our, actually, damn, I didn't show you this. I need to check the scenes more often, darn it. Anyway, slide fail, but whatever. So picosoc, so integrating this here. And the next challenge will be here on the, probably this loads, I guess. Placing this here on the bus, so we, even if this would work to synthesize, adding this to the Verilog code, to the model, to the makefile, synthesizing this with USS, it would not be connected. So we would also need to write our bus interface glue logic code here to interface here with this 32-bit system bus. Probably similar to, let's see if how the simple UART is doing this, I guess. So this would be the next thing here of clock send pattern, positive edge, where is the receive something, simple UART, clock reset something, data. Yeah, in some way we would need to, on the first glance it looks like this is not using this bus, but this is the next thing. So a couple of challenges ahead. But first, of course, it makes no sense to integrate this except maybe for testing purposes to understand how this module integration and instantiation works, especially with a more complicated and complex design like this picosoc. But first I need to get this working in complete perfect order, which was actually this camera view. Yeah, until I figure out where the timing glitches are coming from and I think on this capture you probably see that timing wise it should only have the, or actually does it look slightly better timed? Anyway, maybe this is also HDMI receiver related. I have the feeling it looks slightly less glitchy on the HDMI capture here than compared on my display. But anyway, I hope you learned something. Leave me in the comments below what you think about this. Are you interested in a $100 kind of Pico RISC-V? It's somewhat similar to what the 8-bit guy is doing. I said this already before. I find this project, well, slightly biased, liking my own project slightly more. Of course, it has other constraints. The 8-bit guy, if you have seen this, he's building his dream 8-bit processor or microprocessor stuff. So his prototype costs like $300 or something, and this prototype, even if you buy the all-in FPGA goodness here, even this is only $179 or something, and you only need two, right? So you only need, if we theoretically wanted to produce it like a ready-made, like not with this icebreaker, but if Aston would make a dedicated board with PS2 keyboard and HDMI and without the PMOD, maybe this could maybe be a $99 euro part maybe, or at least 119 or something. And this is more modern, right? So the 8-bit guy is 8-bit with old-fashioned CPU and all the original, potentially hard to source components. And here, not only are we a little bit more state-of-the-art with HDMI output and a 32 like greatest working Pico RISC-V, like 32-bit with working jump instruction, no less. And yeah, sound next will also challenge. We will not have many logic elements left for sound, so maybe I was hoping for something OPL synthesis, so maybe we will not get something better than a PC speaker kind of beeping sound, but yeah. Anyway, or we ask Aston if he can make a board with a larger FPGA. Anyway, we learn a lot of stuff, especially how to do hardware design in practice. Certainly it's, you see, even I did FPGA in university times a decade ago with super small, but you know, in university you do even not necessarily do such complex examples, especially not maybe you do well, certainly not an HDMI output. Anyway, maybe you do some output of some sort, but maybe not with a Pico RISC-V. So, and the complexity even, yeah, it works in principle, it should work maybe, but then some timing glitches. So yeah, hardware is difficult yet amazing. Totally thrilled, super project. I said it before, in my opinion, better time spent than playing Tetris or Mario Run with just jumping with one button. So also super portable, right? If you want some hardware fun on the go like Tetris or something, you go for holiday or something, you can even take it with you, one USB port, and you don't even need HDMI capture. So if you want some fun in your holiday or something, then yeah, 117 just for the Pico RISC-V with serial output, 79 US dollar or euro plus shipping or something. A serial port here over just one USB cable, super portable hacking stuff for FPGA, Pico RISC-V, goodness, totally amazing stuff. If you're interested in this project, if you think this is amazing for Pico RISC-V, has more memory than a Commodore C64, certainly could program some games or small hobby operating system, theoretically some jump and run, something. If you want to help designing any of this, because I will certainly not do this full time, I will probably soon open some Git repository on GitHub, sourcing this Pico RISC-V, sourcing this Pico sock here, and then the HDMI output and gluing this together. And if you want to get into this and help, and if you are more professional and in Verilog and have some tips for this timing glitches and how to do things right, because otherwise certainly only trial and erroring here along. Let's see some more comments in the audience. Sounds like a problem for timing constraints, but that's get ugly very quickly. Yeah, I thought so. Timing constraints. Probably, again, I will most likely over the weekend and some free hour analyze this more. You see that in theory this test pattern works already. We can shortly compute also. Yeah, maybe I next try to also, wait a second, we have here a cool, how many zero drop frames of 30 FPS. Cool retro terminal. For this 80 by 25 is 2K memory, and if we want attributes, that's 4K memory. That is certainly doable, I would think. And if we want, so 640 by 480 is, but you know, we could actually make a high resolution mode with 16 colors similar to VGA. And this would be, this is too much, but divided by 8, that should be doable. Here some 38 something. And for the VGA mode, that would be 320 by 240. That is, or it's 322, okay, that is slightly, it's 76. Yeah, that's getting a little bit to the edge here of what we have available, making this 320 by 200, which is exactly this VGA mode that even a lot of games used back in the DOS days, that is exactly 64K. That is certainly should be doable. And yeah, but first we need to get this stable. As I said, the original example is already off by something. Maybe this original example only worked by sheer luck, and even then it is off by some pixels there. But yeah, That is the progress update here, probably as lengthy as we explain everything here, 40 minutes. Hope you learned something, hope you enjoyed this. If you have any comments, questions, leave them below. Maybe we actually should make here also more generic Verilog instruction for you to better play along at home. But otherwise, leave me below what you think. Well, maybe theoretically, we could even partner there with the 8-bit guy. However, he made it very clear, I certainly watched the videos myself, he made it very clear he intentionally doesn't want to use an FPGA because he doesn't want people to modify it. He wants his fixed 8-bit computer and not like people misusing this for making it an NES emulator. And I understand his reasoning. However, using original old components also not maybe the best long-term idea. And of course, this is more bang for your buck, because with this you can even flash other stuff on there if you don't like. Well, first of all, this is a generic project, so you can do whatever you want with it. And if you don't like whatever we are creating, then you can just flash your NES emulator on there anyway. So I hope you learned something and hope to see you soon for all the next tinkering Verilog FPGA reviews and all the fun stuff we're doing here next to come.